All right. Okay. Good morning and happy Monday. Um, so we will continue on. Uh, I have a lot of like right now my canvas for week 7 is like very empty. I have to post a lot of stuff. I didn't um, do a ton, but I posted your midterm grades and so I want to say a couple things. So you can, if you want to review your midterm, you are welcome to come to in-person office hours or online office hours. And if it's online, I can set up a kind of a breakout room or set up the waiting room so that you can have privacy. The only limitation for when it's online is I can show you your scanned form, the the bubble and form that you filled out, and I can show a blank copy of the exam that has all of the questions. But I don't have like if you did scratch work, I don't have your scratch work scanned. Okay. I only have the bubble and form, and then I have a blank exam. So you can still see the questions and whatnot. But if you want to see your own scratch work, then you have to come to in-person office hours, okay? Because in in-person office hours, I can pull up your actual exam. You can see your actual scratch work. But if you just want to see like which questions I got wrong and what were those questions, you can come to online and you can see all of that stuff. I just don't have like I didn't scan every single person's like individual scratch work page. Okay, I only scanned your bubble in form, so I don't have that. Okay, let me also just pull up the very first lecture. I think I'm pretty sure I talked about this stuff, and I think somewhere along here I put in grades in life, and then I wrote your grades do not define you. And so this is I just want to reiterate this, okay? A lot of you guys did great on the midterm, okay? But some of you did not. And you know, it feels bad. It feels bad to study and then you get, you know, 50%, right? That doesn't feel good. Okay. Um, and and I'm sympathetic and empathetic, and I just want to kind of remind you that even if your score on the exam itself is not up to your expectations for yourself or what you would like, again, your grades do not define you, right? This is just one test in one class that has honestly, in the grand scheme of things, isn't that important. So, I mean, I like my class and I hope you like it, uh, but you know, there's so many things in life that are far more important than this, okay? Of course. Does it feel good to get a bad grade? No, it doesn't feel good, okay? Um, and of course, you know, we want to look at things and see like what we did wrong and how we can improve, but don't you know, don't let this stuff uh, you know, weigh too much on you. Okay? All right. So anyway, um, that's what I have to say about that. I just I think the unadjusted, the raw median score was an 83. So I just added 3 points to everybody's score across the board. So that brought the median up to an 86. And then the grade that you see in the grade book already includes those 3 extra points. Okay, which it's not a I think it's like 1 percentage point in the in the grand scheme of things. But you know, or if even that. But um, but anyway, every little bit helps, right? Okay, let's continue on talking about sampling distributions. So we introduced sampling distributions and the central limit theorem last week, and And so the way the sampling distribution works, okay, is, or the idea behind the sampling distribution is that if you flipped 100 coins and someone else flipped 100 coins and I flipped 100 coins, we're all going to get slightly different results, most likely. Okay, I mean, there's always a possibility we get the same results, but by and large, some of you might get 50% heads, some of you might get 52% heads, some of you might get 47% heads. And certain outcomes like 48, 49, 50, 51, 52%, those outcomes will be likely. Other outcomes are possible, but not as likely, like getting 40% heads or getting 59% heads or 62% heads. Those are possible, but not as likely. And then other outcomes are super unlikely, like getting 70% heads is a very, very, very unlikely outcome. We can approximate that sampling distribution with a normal distribution, okay? The mean, if you're flipping coins, the mean is going to be at 50%, okay? The standard error is given by the square root of p times 1 minus p over n. So with a fair coin and 100 flips, the standard error is around 5 percentage points, okay? And we can use this central limit theorem. That is, we can approximate things with a normal distribution as long as n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. It doesn't work well if p is like 99% or p is 2% and you have a small n. You need to have like a really big n for that to work, okay? Other conditions are that the sample has to be random and independently chosen. And then if you are sampling without replacement, then you need to have a big population. You don't want to sample more than 10% of the population. Again, thinking like a deck of cards, the first card you draw, 50% red, 50% black. But then once you draw a card, what remains in the deck changes a little bit. And we say as long as you're sampling less than 10% of the deck, like fewer than 5 cards, how much it changes, we can kind of ignore. But once you start sampling more than that, then it can cause problems. This is only an issue if you have like a finite population that isn't very big. Most of the times, like you're dealing with a very big population and this thing is not of concern, but it could happen. Okay, so let's just work through an example where we say, all right, let's say I gave you the assignment. Everybody flips a coin 50 times. And I want to know what's the probability we get a proportion of 60% heads or more. Okay, so this would be 50 times 0.6, basically 30 heads or more. So we want to know what's the probability that somebody gets 30 heads, 31, 32, or more, okay? We can approximate this. So we want to know what's the probability that p hat is greater than or equal to 0.6. And we can apply the central limit theorem because all three of these conditions are met. It's a large sample, n times p is 25. N times 1 minus p is 25. Both of those are greater than 10, so that's fine, okay? Coin flips are random and independent, so that's fine. And then we don't have to worry about the big population condition because it's not a finite sample. There's infinitely many possible coin flips, so this is fine. Okay, so as far as doing the math here, we want to use our formula. We're going to say mu is equal to p, so we have mu equal to 0.5. And then our sigma is the square root of p times 1 minus p over n. So we're going to plug in 0.5, 1 minus 0.5 divided by 50. And so this gives me 10707 as my standard error. And so my diagram looks something like this. We have 0.5 in the middle. We want to know what's the probability we get 0.6 or something greater. So we get a z-score. We're going to take in our value of 0.6, subtract off the mean of 0.5, divide by our standard error of 0.0707, and I get a z-score of 1.41. All right, so that's detailed right there. And then I look that up in our reference table. I want to see what's the area to the right of 1.41. So I can look up the area to the left of negative 1.41 as a shortcut. I could also look up 1.41 and do 1 minus that. Okay, so 1 minus 0.9207. And I get, you know, just a fraction under 8%. So if I gave everybody a coin and I said, everybody flip your coin 50 times, figure out what proportion heads you get. Around 8% of you, okay, around 8% of you would get 60% heads or more, 30 heads or more. Okay. This is an approximation, but because again, the true sampling distribution is the, if you remember last week, it's the plots with all of the vertical lines. Okay. But those vertical lines look a lot like the normal distribution, so we can approximate with the normal distribution. And that's what we have. Okay. I want you to try out this next problem. Okay. So this is a fictional thing with approval ratings. Okay, so we'll say in a given population, 42% of people approve of the job that politician John Q. Public is doing. Okay. We're going to select 80 random people. What's the probability that you happen to get a sample of 80 people where 50% or more approve of John Q. Public? Okay. So we've got P equal to 0.42. What's going on? N is equal to 80. So remember, our normal distribution, our mean, is going to be P. And our standard deviation is going to be the square root of P times 1 minus P over N. And the question is, what's the probability that P hat from your sample is going to be greater than or equal to 0.5? Okay. This part down here is just to say that our conditions for the central limit theorem are met, and we can approach this problem. Okay, so I want you guys to take a minute to work on this. Let me also, while you guys are working on that, I will give you your first view quiz answer, which is the letter B. Okay, so work on that. Once you get your answer, you can give me a thumbs up. Ballpark how we're doing here. How we doing? Got an answer? All right, let's start to take a look. So we have n equal to 80. Our p is 0.42. So we plug that in. And so we have our mean is 0.42. And then my standard deviation is the square root of p times 1 minus p over n. And I get 0.0552. We put in 0.42 times 1 minus that, so 0.58 divided by 80. I'm going to take the square root of that, and I get 0.05518 or 0.0552. And so my picture, I've got a normal distribution. The center is at 0.42, okay, because our mean is at 0.42. And we want to shade in everything to the right at 0.5. We get a z-score. 0.5 minus 0.42 divided by 0.0552. So what do I have? 0.5 minus 0.42 divided by 0.0552. You get a z-score of 1.449, 1.45. And so we want to know what's the probability that z is greater than or equal to 1.45. So I'm going to do 1 minus, looking up 1.45, I get 0.9265. So that's going to give me a 0.0735. Around 7%, 7.5%, 7.3%. Yes, question.
The ad is basically just 7% they like gives you to look at.
Yes. So the p hat here is the value from the question that we're looking for. 50% or more. Yes. Okay. Yeah. P hat greater than or equal to 0.5. That's what we want. Okay. So that wraps up what I wanted to cover about sampling distributions and the central limit theorem. And we're going to take the ideas that we introduced there to introduce confidence intervals. I've got a bunch of slides here. We're not going to get through them all, but I wasn't sure how far I was going to get. So I just put them all in here, and then I will take note of when we run out of time, and then we'll continue on. Okay? So the confidence interval will be kind of our first tool of statistical inference. And so remember, the primary goal of statistical inference is that we want to draw conclusions about a population. We're going to draw conclusions about the population based on our observed sample, okay? And so when we were dealing with sampling distributions, we started off with kind of this idea that I give you the coin. We know this is a fair coin, and you're going to flip the coin a bunch of times, and we're trying to figure out, okay, what kind of results we can get. Okay. This time, we're kind of working in the opposite direction. We only get one sample, and based on the sample, we're trying to figure out what the population looks like. Okay. So the example I have here is, what if we surveyed 100 random people and we say, hey, do you use Netflix? Do you watch shows on Netflix? Okay. And I have no idea what Netflix numbers are like. I just made up a number. Okay, so let's say 30 out of 100 people say, yeah, I watch Netflix. Okay. Okay, these are your 100 random people. What does this tell us about the true proportion of the entire population that uses Netflix? Okay. Is that proportion in the population also going to be 0.3? And if I phrase it, is it exactly, is the population proportion exactly 0.3? You would probably say, no, I don't expect it to be exactly 30%, right? I surveyed 100 people and I got 30 out of 100 in my sample. I don't necessarily expect my population to be exactly 30 out of 100, 30%, okay? But if my random sample was 30%, I would expect the population to be around 30%. Like if you told me the population was 27%, I would believe you. If you told me the population was 34%, I'd probably believe you. Okay. If you told me the population was actually 60%, then I'd be like, really? I would be surprised because how did I end up with a sample where it was only 30%? Okay. Maybe I didn't do my random sampling correct, but we're going to assume I did my random sampling correct. And if you're going to tell me the population was 60%, I'm going to question that because my random sample ended up only 30%, okay? So we're not going to be able to get an exact value, okay? But what we can do is we can create a range of plausible values for what we think P could be. Okay, so this is a silly analogy. This is, behold my artwork. This is a picture of a dog standing on a football field. The dog is standing at the 30-yard line of the football field, okay? The dog's owner is also on the field and they're going for a walk, holding a leash, okay? But something strange, the owner is invisible, okay? The owner is the invisible man. And so the question is, where's the owner? Okay. And so the answer is, well, I'm not going to be able to provide a pinpoint location for where the owner is because the owner is invisible. But common sense would tell us the owner is going to be close to the dog. Okay? That's because if they're going on a walk together and they've got a leash, the owner can't be super far away from the dog. That's what we can do. Do I know exactly where the owner is? No. Okay? But we can be confident that the owner is near the dog. Okay? Furthermore, we know some facts and behaviors, facts about the behavior of the dog. Okay? This is a good dog, likes to stay close to the owner, doesn't like to pull super hard against the leash. Okay? Most of the time, the dog stays within 1 yard of the owner. Okay? 68% of the time. 95% of the time, the dog stays within 2 yards of the owner. Okay? And then if you go out to 3 yards, that's going to cover like almost all the time. 99.7% of the time, the dog stays within 3 yards of the owner. Okay? So, these were very specifically chosen. But basically, most of the time, the dog, we're going to say the owner's in charge. Okay? The owner walks, the dog either follows or, runs around or things like that. Okay? Most of the time, the dog stays within, very close to the owner. Okay. So this is the leap. Because we understand the dog's behavior, if we see the dog located at 30, we can be 95% confident the owner is somewhere between 28 and 32. Okay? We can be 95% confident that the owner is somewhere between 28 and 32. Now, it's an elastic leash. The owner could be more than 3 yards away from the dog. Okay, the owner could be at 33.5, 3.5 yards away from the dog. Okay, because as far as 3 yards from the owner, that's 99.7% of the time, but sometimes it does go really far away. Okay, so the owner could be at the 33.5 yard line, but that would be surprising to us because that means this picture was taken at one of those very rare moments where the dog wandered more than 3 yards away from the owner. Okay, because or like 95% of the time, the dog stays within 2 yards of the owner. All right. Sometimes the dog does wander a little bit farther away, but it's pretty rare. Okay. And so we can say something like, I'm 95% confident that if the dog's at the, like, if the dog's at the 30, I'm 95% confident the owner's somewhere between 28 and 32. Okay. So this is, if we're comfortable with this, this is the logic that we use behind the confidence interval. Okay. So the dog and the invisible owner are kind of like the relationship between the sample proportion p hat that we get to see and the population proportion p, which is unknown to us. Okay. So the invisible owner, we don't know where the invisible owner is. Okay. And we don't know the true location of the population proportion p, because again, the population is too big for us. We can't observe the population directly. We don't know what the proportion of the population is. Okay. But we are able to see the dog. We know the dog is at the 30. We are able to get a sample. We are able to figure out exactly where p hat is. We know the sampling distribution of p hat is approximated with a normal distribution, okay? And with the normal distribution, that means p hat stays close to the population proportion p, okay? If the p hat, remember we say p hat comes from a normal distribution where the mean is equal to the population proportion p. We don't know exactly what that is, but we know that's going to be close to that, right? And then we got a standard error formula. So we're going to say 95% of the time, p hat is within 2 standard errors of p. So because of that, we can flip it around and we can say we are 95% confident that p is going to be within 2 standard errors of p hat. So if I see the location of p hat, I can be 95% confident that p is within 2 standard errors of p hat. Okay, so our formula becomes this. Basically, the 95% confidence interval says I am 95% confident that p, remember this is the population proportion p, is going to be between p hat minus, and this is effectively 2 standard errors. And this is over here approximately 2 standard errors as well. Okay, so remember the standard error formula is the square root of p times 1 minus p over n. Okay, and we're basically using that, except we don't know p, so we just plug in our best guess p hat for that. We use p hat to calculate the standard error because we don't know the actual value of p. And then the number 1.96 rather than 2 gives us a slightly more accurate values. Okay. So basically we're going down 2 standard errors and we're going up 2 standard errors. So that's how we make our confidence interval. Okay. This number 1.96, let me talk a little bit about that. Okay. That comes from the normal table, where if I looked up 1.96, 1.96 gives me 0.9750. And then negative 1.96. Negative 1.96 gives me 0.0250. Okay. So if you go to negative 1.96 and positive 1.96, you're going to have 95% down here, and then basically 2.5% there and 2.5% there. Okay, or if you did 0.975 minus 0.025, you're going to be left with 95%. And we can use that same kind of logic to get other values. So if you want 99%, you basically want 1/2 of 1%, 0.005 up there, and then 0.005 down here. Okay. And so the value that gives us the closest to 0.005 is 2.58. So if I look up 2.58, and let me just go to the negative side, that's easier. 2.58 right here, okay? 0.0049. 0.0049 is very close to 0.005. And then so we would get 99% in the middle, okay? And that's basically how all of these other numbers get found. So 90%, you would go 1.645. Like if you look at 1.64 and 1.65, I think one is like 5%, just under 5%, 0.0495, and the other one's just above 5%, 0.0505. And that gives you 90% in the middle, stuff like that. Okay. So this is a good important table here. So these are going to be, what we call critical values. Do we use 1.96? Do we use some other number? Okay, that's going to determine. I want to be 95% confident, or 99%, 90 or 80%, things like that. Okay, so to generalize, our confidence interval goes from p hat minus, and then not necessarily 1.96, maybe some other number, 2.58, 1.645 times our standard error, okay? And then we do the same thing, p hat plus this. Now, because these two formulas are almost exactly the same, and the only difference is that we have a minus and a plus here, we can combine these into a single symbol, okay? And this is called the plus minus, okay? So this is plus or minus. Sometimes just called plus minus, okay? P hat plus minus Z star times the standard error, okay? And that quantity, Z star times the standard error, is also known as your margin of error, okay? Margin of error is, I don't know, a term that we often hear when regarding polls and stuff. It'll be like so-and-so's approval ratings are, 40% with a margin of error of 4% or something like that, okay? So that means the true value could be anywhere between, or we're really 95% confident the true value is between, what did I say, 40% with a margin of 4%? So 36 to 44%, okay? So, you hear that, margin of error. Okay, so let's work through the calculations for our Netflix example. Okay, we said we surveyed a sample of 100 randomly selected people, so that's our n. N is equal to 100. 30 people in our sample said, yes, I watch shows on Netflix. Okay, and so we have x equal to 30. So our p hat, my sample proportion, is going to be x over n, 30 divided by 100. I get a p hat of 0.3. And we say, okay, well, does that mean exactly 30% in the population watch Netflix? And we said, no, not exactly 30%, but probably something close to that. Okay, well, what does close mean? Well, we're going to have to go p hat plus or minus z star times our standard error, which is the square root of p hat times 1 minus p hat over n. Okay, so we have p hat is 0.3. For a 95% confidence interval, that means z star is equal to 1.96. And this is just from the previous table. 95%, we use 1.96. This is going to be the case always when we're dealing with proportions, okay? And then our n is 100. So we're going to plug in 100 for n. So plugging in our values, p hat minus, I get 0.3 minus 1.96 times the square root of p hat times 1 minus p hat, 0.3 times 0.7 divided by 100. So my calculation, I do 0.3 times 0.7 divided by 100. I'm going to take the square root of that, and I get 0.0458. So I get 1.96 times 0.0458, 0.3 minus that. So I get 0.3 minus, and I multiply 0.0458 times 1.96, and I get 0.0898. So 0.3 minus 0.0898 gives me 0.2102. So basically like 21%. And then the nice thing is that all you have to do is just change the minus to a plus. So from 0.3 minus, I'm going to do 0.3 plus 0.0898. That's going to give me 0.3898. And so my confidence interval becomes, I am 95% confident that the proportion of people who watch Netflix in the population is between, if I round off, 21% and 39%. Basically, we have a sample proportion of 30% and a margin of error of 9%. And so what do you think is the proportion in the population? So I'm 95% confident it's going to be between 21 and 39%. Okay. So we have interpretations here, okay? So my confidence interval, we would write something like this. We would write my 95% confidence interval is 0.210 to 0.390. No, sorry, should be square bracket on the right-hand side. Okay, and so I'm 95% confident that the proportion of people in the population that watch Netflix is between 21 and 39%. So I can draw a number line here. Okay. And basically I'm saying I'm 95% confident that we're between here and here, okay? Okay. So again, it's kind of like, where's the owner? Where's the invisible owner? And we don't know, okay? But we see our p hat is at 0.3, and based on that, I'm 95% confident the owner or our population proportion is between 21 and 39%. So the question could then become, okay, we could say, do we have evidence that the proportion P is different from 20%? Oh, hold on. I want to copy this. Copy. Paste. Okay. So where is 20%? 20% is over here. Okay. So we're going to ask, do you think P is 0.20? Okay. And our answer is no. I'm confident P is in between 21 and 39%. Okay. So you gave me a number that I don't like. It's outside of the range, right? 0.2 is outside. So 0.2 is outside the interval. Okay. Meanwhile, I'm 95% confident P is inside the interval. Okay. So I would say I am confident P is not going to be 20%. Again, it's kind of like if you see the dog standing at the 30-yard line and they say, do you think the owner is standing at the 34? And you say, no. I know the dog likes to stay within 2 yards of the owner. I'm confident the owner is not going to be at 34. Okay. Now, could we be wrong? We might be wrong. But I'm pretty confident. I'm 95% confident. Yes.
Consider both like 80%. Could we still say that they're confident at 0.2 is about 20% of the time? It could be about 500.
So, so if I make an 80% confidence interval, I will still say 20.2 is not in our interval. So we'll probably run out of time today, but I'll show you examples of like what happens when we make different levels of confidence. Okay. Okay. So basically the conclusion here is we created our confidence interval based on the data we have. Okay. So this confidence interval doesn't come out of nowhere. Well, it's based on the data. I've surveyed 100 people. 30 people say I use Netflix. Okay. So based on that data I've collected, I'm feeling good. I'm feeling confident that the proportion in the population is not 20%. Okay. Because it's outside of my interval. All right. So I think that's detailed here. Yes, 20% is not between 0.21 and 0.39. It's not considered a plausible value. We say we have evidence that P is a value that's different from 20%. Okay. Okay. Do we have evidence that the proportion P is different from 25%? Okay. So I wrote, I'm confident that P is in here. What about 25%? So 25% is right there. Okay. And so now 25% is inside the interval. 25% is a plausible value. Okay. It is inside. It is inside the interval. It is a plausible value. So this is one of the frustrating and annoying parts of statistics and confidence intervals is we have to use all of these double negatives and we have to say the phrase we use is we cannot say that we have evidence that P is a value different from 0.25. Okay, it's very annoying. We can't say that it is 0.25. We have to say, I don't have evidence that it's different from 0.25. Okay, that's not the same thing as saying it is 0.25. We're saying I can't say it's different from 0.25. Is it 0.25? I don't want to say that. Can you say it's different from 0.25? No, I can't say that. It's a little bit, you know. That's what we say, okay? All right, and then kind of going along with that, do we have evidence that P is equal to 0.25? The answer is no, okay? 0.25 is a plausible value, is plausible, but we can't say P is exactly. We can't say P is exactly 0.25. Okay. And that's going to be one of the whole things of statistical inferences. We'll never be able to say the unknown value is some exact number. Okay. It's like where's the invisible owner of the dog? We cannot say exactly where they are. All we can say is I'm pretty confident the owner is somewhere in between here and here. But we can't say for sure they're at 31.2 or for sure they're at 25. Okay. All we can say is based on what I know, somewhere around here. I forgot to do my job of giving you answers, right? Okay. Second answer, if I remember, is B. Third answer is A. Second answer is B. Third answer is A. Okay. There's more to say about confidence intervals. So we will continue this on Wednesday. And then again, if you want to see your midterm, come by office hours, in person or online. In person, you can see your actual exam. Online, I can just show you your scan form and the blank exam. Okay, that's it. Have a great rest of your day.